Okay, today we're going to talk about applications of exponents and logarithms. And for this, we're going to show you two types of exponential growth and decay. Okay, so what we're dealing with is some amount equals the beginning amount times e to the kt power. Now this constant, if it's less than 0, then we're dealing with decay. And if it's greater than 0, then we're dealing with growth. And what we generally have with these problems is you have two sets of data. The first set of data is for a general problem, and the second set of data is for a specific problem. Now the general data will be missing that constant k. And so we figure out then what the constant is, make a formula that applies for that situation, and then use our specific data to find the real question. Okay? So let's look at what that looks like with this problem. This is based off some actual data from the 2000 census. Okay? In the 2000 census in Winfield, Kansas, there were 2,007 school-age children. By 2010, there are 2,258 school-age children in Winfield. And we want to know, in what year will the number of school-age children reach 2,500? Okay? So, how we set this up, I'm going to zoom in to create some more room for myself here. We know that our ending amount was 2,258. The beginning amount was 2007, and that's e to the k times 10 years. So our time was 10 years in between those. Okay? Now we need to solve for k. So what we're going to first do is divide everything by 2007. And so then e to the 10k equals 2,258 divided by 2007. Now, in order to get to this k, we need to take both sides of the equation and apply the natural logarithm function to it. So that's what this will then look like, is we'll take the ln of both sides of this equation. And that will leave us with 10k equals the ln of 2258 over 2007. And so k then equals the ln of 2258 over 2007 divided by 10. And when you plug that into your calculator, you find that that number is equal to 0.001178. And we can use this constant to set up an equation that models how many children are in Winfield, Kansas. So our amount is going to equal 2007 times e to the 0.001178t. Okay? So that is the equation that models the actual number of school children in Winfield, Kansas. Okay? Doesn't do anything else, just that. Now we want to know when that ending amount will equal 2,500. So we plug in 2,500 and we're going to solve for the t in that. Okay? And again we're going to divide by 2007. So we'll get 2,500 over 2007 equals e to the 0.001178t. And we'll take the natural logarithm of both sides again. And so the ln of 2,500 over 2007 is going to equal 0.001178t. So t will then equal the ln of 2,500 over 2007 divided by 0.001178. And when you plug that into your calculator, we get 18.646 years. So in approximately 2018, we will have 2,500 school children in Winfield, Kansas. Now, that was an example of exponential growth. Notice that our K value here, why do I keep drawing that? I don't really like that. Our K value here is positive, very slightly positive, but it's still positive. So therefore, we're having growth that occurs. Now, this is another example from the news. They found King Richard III's body under a parking lot in England. And we want to test to see if what they found was, in fact, King Richard's body. The bone that they found contained 85% of the original amount of carbon-14. Now, carbon-14 has a half-life of 5,568 years. Okay? That means if a sample is weighed after 5,568 years, there's going to be half of it left. We want to know what's the approximate age of this bone so we can determine, was it really from King Richard III? Okay? Now keep in mind, King Richard III died in 1485. So if this is 2013 minus 1485, the age of his bones should be about 528 years. Okay? Now, using our formula, we know that the ending amount will be half the beginning amount. Okay? And this is going to be e to the 5,568 k. Okay? So if we divide by a, we get 1/2 is equal to e to the 5,568t. Again, we can take the ln of both sides, and we get the ln of 1/2 is equal to 5,568t. So t is equal to ln of 1/2 over 5,568. Plugging that into your calculator, you get negative 0.000124. So that is good because we expect decay. Our specific equation will end up being A, or our ending amount, equals our beginning amount times e to the negative 0.000124t. Now, this specific bone contained 85% of its original carbon-14, so 0.85 of its original amount is equal to e to the negative 0.000124t. And I just divided those a's out of there, is what I really did. Okay? So if we take the ln of both sides, we get ln of 0.85 equals negative 0.000124t. So the ln of 0.85 over negative 0.000124 equals our t. And that t, when you plug it into your calculator, comes out to be 1,310.64 years old. Now, we expected something around 528 years. And the carbon dating suggests that this bone is actually 1,300 years old. So, therefore, it could not be from Richard III. It's from someone actually a whole lot older than Richard III that died a whole lot of time prior to that. Okay? So, that is one way that carbon dating is worked. And it is very mathematical in nature. So, hopefully we'll enjoy some of these problems, and these are some of the more useful problems that we'll see a lot in science and math as well.